Slide off. We take the website. Okay, now it's my pleasure to introduce Monica Vazirani, and she's going to tell us about Skeins on and tori.
Thank you so much, and it's a real delight to be here. My first time in the area. Hopefully not the last of the amazing conferences you're planning to continue to organize. So thank you so much for putting this together. So this is all joint work with Julia Bierent, David Jordan, and Matthias-Vancraeynest. They're all at the University of Edinburgh. Julia and Matthias are students of David's. They're probably going to be on the job market at some point soon if you want to keep an eye out for them. And then I don't know about how these slides is going to work with seeing things. If there's anything you can't see in them, just let me know. So rough outline is what we're going to talk about. Skein algebras and Skein modules, starting with the SL2 case. And my notation for Skein algebra and Skein modules abbreviated algebra SL2 if I mean SL2. And work towards GLN later. The mapping towards what is that? I didn't know when we started the project. I'm not a topologist. I had to have it explained to me. And some examples done. And then the point is really the Skein module, whatever it is, it's a vector space. Saying what its dimension is and having some nice combinatorial formulas for it is the goal at the top. And then depending on time, some of the ingredients that go into proving these formulas using Hochschild homology and a bunch of irreducibles and to make some computations. And a gentle introduction to Skein algebras, but I have to try to speed through it as well to leave time for everything else. So I think most of us are familiar with diagrammatic algebras and maybe even diagrammatic categories, and everything I'm going to say is a K-linear. My K is going to be C rational function over Q, so Q is generic. A lot of people in Skein theory care about Q root unity, but we're doing Q generic. And so you might have some way that you draw pictures in an algebra, like the group algebra symmetric group. Opposition is by stacking. And then, of course, if you're going to go back and understand what you're getting and not get something infinite dimensional, there's probably a bunch of relations. For instance, symmetric group, we have braid relations and quadratic relations. But there's many other diagrammatic algebras out there. So, for instance, well, there's the braid group itself, which we already mentioned in the conference. And of course, I'm doing type A. Everything's type A. So, S1 S2 S1 equals 2 S1 S2, and that's it. You don't have a quadratic relation for the braid group, but of course, the symmetric group is a quotient braid group, or corresponding to algebras quotient there. But instead of taking the usual quadratic relation that you do to get the symmetric group, you could deform that quadratic relation a little bit at Hecke algebra. And so I haven't actually written out equations, but just drew pictures. So depending on how you like to best think of your quadratic relation, say, if you wind it twice, you get the identity picture plus one crossing with a coefficient. That's where my Q comes in, Q minus Q inverse. So when Q equals 1, it gives a relation to symmetric groups, and indeed you get the group of the symmetric group. Depending on how you like to think of it, maybe overcrossing a positive crossing minus negative crossing is equal to, again, it's Q minus Q inverse times no crossing, or you can think of it as basically writing minimal polynomial equation that these two expressions multiply to 0, and they're up to scalar, they look like item points, in fact. Okay. Another diagrammatic algebra you might have seen is typically lead algebra. And maybe that's even, maybe when you learn the symmetric group, you learn it in group theory, you don't even draw pictures. But you probably, if you're going to learn something to lead, it's probably first you use pictures. And so what we do, we find temporary algebra for n, the n dots on the top and bottom, and I connect them in all possible ways that I would not allowing any crossings. Crossings or non-crossing, and if you connect them up, and then the diagrams that you get, you might know that to count them, that's the same as the Cavalier numbers, and that's in bijection when you look at Richard Stanley's book. You know, at some point there was like 120, but I think if you look in newer editions, maybe it's like 200 different interesting combinatorial things. triangulations of the n-gon, n plus polygon. Maybe to cluster people, that's more exciting thing that you're counting Catalan numbers. But of course, if you stack these and make an algebra, so again, if you like stack two of these on top of each other, you can create closed bubbles in the middle, and you just chop them at the expense of getting negative q plus q inverse or negative two there. And for the temporally leaf algebra, you can do just as I said, but you can also view it as a quotient of the Hecke algebra by saying, well, in the Hecke algebra, I have crossings, positive and negative, and you can say, okay, I decide that this positive crossing is this expression of diagrams with no crossings, or the coefficients, Q. But the way that I often think of it is that this funny cut cap diagram that doesn't exist for the symmetric for the Hecke algebra, there everything's directed. And temporally leave, you're like, oh, things are wind around and tangle and move, and you just use isotopy, and then you can get rid of crossings using that diagram. So I think how do I make sense of cut cap in Hecke language? Just write out what you get, and up to a scalar, a quantum negative quantum 2. This is an idempotent. Well, it's clear that this is an idempotent. You do it, and there's double pops, quasi-idempotent. This is when you have to take a slightly different quadratic relation on the last slide. For the Hecke algebra, that if you just tweak your generator by the powers of q to the half, then this is up to this minus q inverse is the sign idempotent for the Hecke algebra. And the sign idempotent, they have on control what's to come. Okay. But where did the relations come from for temporally leaf algebra? Or you can the Hecke algebra. One big motivating place is Servile duality. So if we're looking at GLN or SLN, and I really want to, if I'm going to do Hecke not symmetric group, I really want to talk about the quantum group, which is finite dimensional representations. Or you should take RepQ GLN or RepQ of SLN. If you take the defining representation, so when I see V, especially if it's blue, I mean I'm defining representation. That's sort of a GLN. So it's n-dimensional. And I take D tensor copies of it, and then I have a map from the Hecke algebra on the strands to the endomorphisms. And it's not an isomorphism always. There can be a kernel depending on how large D is compared to N. And if we were to think about the variable representations of Hecke algebra, like so the symmetric algebra is indexed by partitions, you have to throw away the partition more than any part. If we're used to lead theory, right? You can't make standard tableau with filling or semi-standard tableau fillings using 1 through n if you run out of boxes. Okay, and so it's really that if you get a sign idempotent that's too tall, that's really what's being killed when you want to do SL2. If you keep that in mind, it's a good mindset for going from SL2 to SLN. And again, my true sign idempotent symmetric group, this is alternating some partitions, and it has its own cuneiform analog. Okay. So, okay, another place where you might think of these relations, where they come from, is if you look at these not invariants and like Drive, where drawing these pictures and even working towards Jones polynomials. So my blue strand is defining representation and SL2 is homology. And when I do a crossing, that is really representing an R matrix. There's a map from B tensor B to B tensor B. And again, depending on where you're living, if you want the crossing to mean that, or you want to compose with, the swaps the places. But we're just going to think crossing means R matrix. Then this cut cap is well, it's another map from B tensor B, two dots of C tensor B. It's the one that factors through, well, B tensor B to the second exterior power to itself. If we make it an idempotent, so there's actually make it an idempotent, but again for a scalar front using negative 1 and 2, it will correspond to this projection. then also diagrammatically, it makes sense because for SL2, this is the trivial representation. And so it kind of, but there's this midair waste, and nothing is, that's where trivial is living. So it really is B to B to trivial and trivial to B. If it was GLN or GL2, not SL2, this wouldn't be trivial, it would be determinate, and that will come up later, because then we can focus more on each. Okay, so, right. So our matrices, that means I'm being a little fancy with my SL2. I'm using the fact that QSL2 is a graded ribbon. And then a lot of, when you do Skein theory, what you really need is some graded ribbon category as what's labeling your strands, and even having fancier morphisms there. But I'm going to be very vanilla with Skein theory today. So for instance, yeah, so even with SL2, you can have more interesting strand labelings going on, and I'm not going to do that when I'm only going to label things with a defining representation. And I can get away with that because if I care about finite dimensional representations of either SLN or GLN, if I have the defining representation, I tensor together an F10 with itself, I can find finite dimensionals, a direct sum in there, and I'm still looking at fusion. So I can get away with that as long as I draw enough pictures.
Okay. You need the ribbon structure at this point.
What about the, I didn't say anything about the ribbon structure yet. Yeah, because we temporarily leave, yeah, no. You could deduce it. You could deduce the ribbon structure from, knowing how to resolve the crossing and make a crossing list. Deduce what that is. But yeah, and when you go to Skein theory, you have tangles, so you can encounter ribbons. I don't understand that. Yeah, I don't spend much time on ribbon aspect of it. Okay, so you might have also heard these SL2 relations. If you, again, give your constants slightly different names, draw the relations slightly differently, you might have heard Kaufman bracket Skein relation. And so, or Kaufman bracket Skein algebras and Kaufman bracket Skein modules. And so then you have some ambient 3-manifold, and then you're drawing all kinds of things you can with isotopy, and then you put in these SL2 like relations, and then see what you get. Okay. And so I drew a couple of 3-manifolds when I draw it in. So what we're doing typically lead algebra, we're really thinking of drawing it in 3-manifold. I is my interval 0 and 1 set, in this cube, and then of course we decide, okay, however many dots top and bottom. Or you could say, don't have any boundary conditions whatsoever and still draw the tangles. And so in what sense are you going to get an algebra to change it from the cube to something else? Well, if the manifold that you're in has the form surface cross interval, that gives, well, we said composition static. So if we're taking a fancier 3-manifold that is the form surface cross I, we get an algebra structure. So you can just stack I on I. Whether you can do other kinds of stacking. Okay, and so that means that if I have a surface, I get a Skein algebra decorated by SL2 on it. If the 3-manifold is surface cross I, and I have my SL2 relation with Kaufman bracket. If you have a 3-manifold though that's not something cross I, so you don't necessarily have an algebra structure, well, we can still study that, and we're just going to call that a Skein module. Don't worry if it's a module for what algebra. I can say Skein vector space and say it today. So Skein module, I don't really care today about anything about the structure of it, but except for this vector space. The point is to get dimensions of these. Why? Oh, because I'm a combinatorialist. The dimensions are numbers, I care to count. Okay. So let's see. Oh yes, I'm sorry. So I'm often really terrible with remembering to cite people, so let's put on the slide. So the beginnings of Skein algebras and Skein modules introduced by Steve, whose name I pronounced terribly, sorry about that, to try it back in the late 80s and early 90s. And if you look at looking more at things like webs, moving into XLN, Sephora 2005. It's a good reference for that. Okay. So you can make not just an algebra module, you can make a category. So you study the temporary algebra, maybe have a temporary category, a temporary category. And so what you change your point of view a little bit, and you think these dots, or even having no dots, as objects. That's okay, because there's like V tensor V tensor V tensor V, so we just think of these objects. And what are the morphisms in your category? Well, morphisms are between objects. You just take any collection of dots here and any collection of dots there, and you draw these lines between them to isotopy and satisfying, your relations. And so instead of just having three dots you have, or sorry, people tend to go up. Instead of one dot to one dot, you do 1 to 3, or 5 to 3, and so on. But there will be parity issues. You'll get 0 otherwise. And you can still stack and compose your morphisms, and of course endomorphisms will, all right, so all of these algebraic gadgets, Skein algebra, Skein category, Skein module, or if you want to think Skein vector space, given your three manifold, or even just take the dimension, you can think of them as algebraic invariants of the topological space. As you the surface, do the surface cross line of the three manifold to start with. And so that's how I like to think of it is, oh yes, it's something that's on the right, but it's also a gadget that you stick a manifold into and you spit out something different. So it does, if you work with TQFTs, Skein theory fits in for that realm very well. Okay, now of course, SL2 is the great place to start with your warm-up, and then once someone does something for SL2, you have to say what about SLN, or in fact, any reactive group. And you can make sense of these notions. And like I said, any group of gradient into category also fit in it's happening in Skein theory. And so, K-linear. So we can do Skein theory there, but again, today we only need to understand G GLN theory. All right, so let me tell you the theorem of Gunningham-Jordan-Safronov is that if I take M to be a closed oriented three manifold and G a reductive group, so that means when I make my Skein category, etc., I'm going to be using reduction G. And Q has to be generic for this. Again, Q root of unity, there's lots of stuff in Skein theory about that. Just doing Q generic. If you take that Skein module for all the tangles and take the relations that you get, be different relations now, depending on what, that would be finite dimension. So that was a conjecture of Witten that was produced by this group of people. And so then David was like, okay, great, now we know it's finite dimensional. The proof is very not constructed. So you want to say, let's compute these dimensions for various three manifolds and interesting G. And at that time, not that much was done. So these results are taking advantage of this theorem and saying, let's see what we can actually do. And you could say, do I really need it to be closed? Just a quick cartoon of an example. Let's say you're with annulus cross I, so the boundary there, and you think about it, right? You could draw a Skein that just kind of runs around the puncture of the cylinder, and you could stack a whole bunch of those on top of each other, and I don't think relations are going to get you anywhere to kill anything there. You could see that you get something in fifth dimensional. So what were some results though for this? Well, for SL2, again, SL2 is very well studied, so lots is known for SL2. So if your three manifold is sphere cross S1 or three torus, in fact, any a genus G surface cross S1, configured for that. But 2019 was not long ago. Also work, Gilmer-Mossbaum and Tree Wolf. Also for the mapping force I'm going to talk about today for SL2. Yeah, here's that.
Sir, can you explain what closedness has to do with the not looking like the annulus not crossing interval?
Oh, it's okay. Again, not a topologist, so I guess it's more. It's just, let's see, this is more like, here's an example of something that I knew that wasn't closed and I knew it wasn't finite dimensional.
And why is it not closed?
Oh, sorry, because it has a boundary. Yeah. So like this, like a circle is closed as a one manifold, but like an interval wouldn't be. And so as a three manifold, right, this isn't closed.
Oh, okay,
But like a three torus is closed.
okay.
And yeah, I'm not saying, yeah, and I'm not necessarily, like, I didn't say something about like high one and having punctures that can run around, but that's the problem. So it's not that. Yeah, so I can't, I mean, for this example, it's more like I can see that it's not, I can't really point about what it is about being closed or not closed in this particular.
No, sorry, it just, the understanding that you meant that there shouldn't be boundary, I'm also not a topologist, and so, I can be easily confused.
All right, so lots of these computations again have been done for SL2. And even though this isn't a dimension of the Skeins module here, I did want to point out that from yoga did a lot with the two torus and understanding the structure of the Skeins algebra for SL2. But not so much for other G. All right, so my focus is on G GLN and M is mapping torus, which I will explain, because again, like I said, I had fun that explained to me. And I'm not just going to compute the dimensions, I'm going to package them all in a generating function of GLN as M varies. Okay, and have some formulas for that, and then some understanding of that. And we don't have these results for SLN mapping torus and inclusion of plain old. Okay, so what is a mapping torus? I'm going to start out with what is a mapping cylinder. Okay, so a regular cylinder, how do you make a regular cylinder? You can, take I cross I and then glue up, right? But another way to think of that is I have an interval across the circle, and I've identified, I identified an X here with, well, same X there. So I can think of it as I have some diffeomorphism gamma from the interval to itself. And, how do I get the circle? I take an interval and I close it up. Great. But when I do that, I want to twist and identify X with gamma X. So when it's the identity, you're just crossing the circle. And, you draw it by identify two signs. What happened? Did I take a chord?
No.
Okay, great. Okay, so the next thing you can do is say, okay, well, let's take a different diffeomorphism, one that takes X. Well, if my interval is 0, 1, it's X to 1 minus X, but if it was centered on the origin, it'd be like X to minus X. Well, then, right, instead of having both arrows pointing this way, our way of identifying, like doing that, and of course, as you know, you'll get a Mobius strip. And so, okay, so that's mapping. That's two examples of mapping cylinders. Yeah. So a mapping torus, do the same idea, right? So how would you get a regular free torus? You do two torus cross circle. And then crossing with the circle means you cross an interval and wrap around and identify with the identity there, but instead put a diffeomorphism with the torus there. And if gamma is that diffeomorphism, I'm calling that the mapping torus and so gamma. And so some things, so if it's just the identity, again, so my drawing skills are not great, plus I'm not sure how good your topology is. So if we draw our two torus as a rectangle with these sides identified and those sides identified, then the easiest way to draw torus cross I is just as a cube. But of course, these sides are identified, these sides are identified. If I'm crossing with a circle, then these are also identified. There are three torus. And so diffeomorphisms of the torus, well, if we're looking at what we get from n gamma, we can just take gamma to be something in SL2Z and up to conjugation. So you can imagine that conjugation isn't going to change when you glue things up, because these two guys that you're conjugating by are going to meet each other and cancel each other out. Okay. So if I want to study mapping tori and gamma, I really just have to look at conjugacy classes inside SL2Z. That's what I'm going to do. And right, what if you tried, okay, I don't know how to picture other mapping tori other than, I don't even know how to picture the three torus, honestly. Other than, okay, but let's say your gamma was negative identity. So that means, so I will imagine now the origin being the middle square, so x identified with negative x. And then when you go and you glue it up, you have to take that into account. Well, if you think about x to negative x, oh, that's just a rotation by pi. So you just have this three torus, you rotate by pi, and then you glue it. Of course, what you're gluing isn't a rectangle, it's a two torus, because these sides are identified and that side. So another way you can think of it is if you drew the meridian and longitude of the torus, that's the torus at the top and the torus at the bottom, and you draw the meridian and longitude on that, but you know, when you glue them up, meridian to meridian, this meridian is going that way, and this meridian is going that way. Let's say the longitude is going that way, now it's going that way. That's how they're coming together. So that's it. Or if your SL2Z matrix was like 1101, the shear, often called capital T, like the generators T and S, but that's not to be confused with T of torus. You could think, okay, I'm going to move my longitude and what's the top and the bottom torus that you moved up to. Well, meridian is the same, but longitude is just doing the plane wrap, it winds around once before it wraps up, and those get glued to each other. That helps you to picture what mapping torus is. Okay, so that's the mapping torus side of things. Now I have to do skeins for G GLN. Well, just like with SL2, I want to just have all my strands be blue and not labeled with the other potential representations of GLN. I'm going to do that again here, which I can get away with. And my crossing is still going to come from an R matrix. So my crossing relations for blue strands, just like your Hecke relation, that's like a sure by as well. You think variable equal, positive crossing minus negative crossing, Q minus Q inverse times no crossing. Okay, so now if you pose up a loop, you get quantum n times nothing, because quantum n is your quantum dimension for your defining representation. So that's taking place of quantum 2 in the SL2 case. Now, when I say, wait, that was negative quantum 2. Well, technically, that's something that temporally leave versus SL2. So SL2 usually is positive quantum 2, and for temporally it's negative quantum 2. But if you change the ribbon structure for SL2, you can make the negative quantum 2 if you want. But we're just going to take positive quantum here. So if you're asking with the ribbon structure, if you do a little loopy loop, positive crossing there, you go Q to the n times it, so on. Now, I also have these funky red dotted strands that don't see with the SL case. And where do they come from? Well, right, we mentioned that if you do V to tensor n into wedge and V into tensor n, if this was SLN, this would be the trivial representation. And it would be like the nothingness. So you'd have kind of n strands coming into nothing and out of nothing n strands. But well, we have the determinative representation, and it's really a useful, important, even though it's one dimensional representation. After pseudo, we need to represent it some way. Well, that's what my red dotted line is, determinative representation. And it turns out that it makes life a lot nicer for GL than for SL. Somehow the fact that the determinate strand, when it passes through other strands, it kind of Q commutes with it. That Q commuting is responsible for a lot of relations that collapse down and make the skein algebras a lot easier to handle, make the dimensions smaller than the SL case. Okay, so basically she thinks the red strand is a determinate strand and it passes through things at the expense of Q.
So the coupon sigma means you choose a minimal representative.
Yes, sorry, I didn't. So yeah, so you should think here, this right-hand side formula, you should think of how would I write determinate representation? You can say, well, I can just take my sine idempotent. How do you write your sine idempotent? you use sure biodivality, you write the basically as a sum with the appropriate alternating powers of Q of all of your anti-critical permutations, and then you can just take a positive of all of them as long as you have the appropriate power of Q. Any way of writing your sign item potent. If you wanted to expand into bigger pictures, do that. So this takes the place of the cut cap was the appropriate power of Q to the positive crossing. But it's the SL versus G. Okay, so now we have our ingredients, our mapping torus, which is our ambient free manifold we're drawing these skeins in. My skeins are a bunch of blue strands and some red dotted strands running around inside, and we saw what your relationships are. And now we want to say, what's the dimension? Package it as a generating function. Very happy combinatorial thing to do. Positive numbers in a generating function. What can be said? Okay, so a lot of detail on the slide. So this is with Julia and David. So we have a very nice product formula or their expansion of these. So, you know, 1/1 minus t to the k, that expands really well. 1 plus t to the k plus t to the 2k plus t to the 2k and so on. And then to some power, and we blend those all together. And these exponents, we see k and gamma, they're all positive, non-negative. They're actually all positive integers, and we give them explicitly as, and that kind of only if the trace isn't plus or minus 2, it depends only on the trace of gamma. That gamma was your matrix from cell 2Z. And so that's the broader answer. What if the trace is plus or minus 2? Well, really the only problems are, so your conjugacy classes in SL2Z, some of them look like, you know, 1 something 0 1. These matrices that don't have distinct eigenvalues and aren't the identity or negative identity. Yeah. And so they have a slight different, they have an easy formula, but they just don't quite fit in the same as the other ones. Basically, because of that Jordan blockiness to them, they behave a little different.
What's the growth of the CKs?
What
When you say that they depend on MNK, what is the growth of CKs? It's linear, quadratic?
linear, it's like n times k.
Okay. Mhm.
Okay, yeah, so here's the CKs. So what is CK? So if I have something really, I said trace not equal plus or minus 2. I really mean not conjugate to that 1m01 or -1 m prime 0 -1. As long as you're not conjugate to one of those, this CK is this funny sum. So 1/k, sum of the divisors of k, Euler P function, times the absolute value of the trace of gamma to that d, that divisor of k, minus 2. We sum all that up. And where does that formula come from? Again, if I sum over dividing an Euler P function, I guess I could have written it as you could sum it from numbers from like 1 through k, trace of gamma, that power. So not a relation there, but it's wanted to package it this way. It comes from an orbit count. Basically, if there's like, you know, sort of a cyclic group action happening when you do an orbit count, if you get forming stuff like this, cyclic groups and stuff. And why is it just depending on the trace of gamma? Well, the trace of gamma to the D is a Chebyshev polynomial of the trace of gamma. So really, you just care about the trace of gamma. So that means that I have two matrices in SL2Z with the same trace that's not plus or minus 2. They're generating functions for the dimensions Skein. Algebras from G GLN will be identical. All right, and what do the C's look like in the other case? Well, if gamma is the case, the identity is just 1. So then, yeah, we have if your beginning gamma is conjugate to 1n01, then it would be the absolute value of that times k. Because it's basically, right, if we take this matrix for k power, there's km there, and that's the important information that we're taking. Okay. If it's actually conjugate to negative on the power of the shear. It depends whether k is even or k is odd. It's k over 2 in the even case and 4 in the odd case. Okay, always happening that way. All right, so in particular, right, if we were to have gamma be the identity, then my mapping torus is just the regular 3 torus. And if you look back at that formula, when it was the identity, we always got 1. So you put always 1 here, so it's 1 over 1 minus 2. Here always with 1, so you expand it out and you say, I know that generating function, that's the generating function for the partitions of it. And so I could say as a corollary, but that's not how it works. But if we knew this theorem and didn't know anything else, a corollary for this would be the GLN Skein module of the 3 torus has dimensioned the number of partitions of it.
Okay, I guess it didn't parse like the formula in the previous slide. Does
Yes.
this CK grow like is it like monotonous as it grows?
So
No,
this growth is it gets if the trace of let's say the trace of gamma is like 4, then the trace of gamma to the k is going to get bigger and bigger and bigger and bigger. Because I think that just happens with it because it's an SL2. Yeah. So the trace, well, that'd be positive. I think when you have positive trace, a trace bigger than 2 in SL2 and take bigger and bigger powers. Well, let me just say this. Let's say you took a matrix of all positive entries. Okay. And then I have a positive trace, you would see the trace getting bigger and bigger and bigger over time. And then, so then this would keep growing quite big. But yeah, we haven't done any, I'm not like an asymptotic growth kind of person. So it didn't even occur to me to ask how big that is growing.
Yeah, it's fine.
Yeah, we'll see a slide maybe with an example. We just took a random matrix like trace. Here was trace 4 and trace 3, and you see the numbers growing pretty fast. Okay. What if we took the shear 1101, this one that it has this other kind of growth? Well, then my CK is always K, right? Because my M is 1, otherwise it would be MK or absolute value of K. And so if that means the formula, whatever one of my CK is K, you expand that out. And depending on where you are in combinatorics, you might recognize that as the generating function for the number of plane partitions. Of that. Now I'll picture of plane partitions in a moment. Now you might think that means there's other wonderful funky combinatorial gadgets that go with all the other matrices. Not that we found yet. Maybe we need to go into LEIS a little more and do a little. So I don't know that there are other nice recognizable generating functions in the other cases, but these are the 2 nicest ones. So partitions of n, so integer partitions. Yeah, just writing a number as a sum of other positive numbers. Or if you don't like drawing boxes, you could just like draw the plane and just have a bunch of dots with gravity going this way and that way. Why did I do it that way? Because to motivate, what if the plane partition is just a 3D version of a partition? You just have to have gravity pushing you down, and drawing those to actually look like stacks of blocks and cubes and getting perspective right, or even finding a program to inform you. I was way too lazy for that, but I can draw a bunch of dots. So we have this 1, 3, 6, 13, and so on, and these are plane partitions. Okay, so, oh great, I still have time, yes. Okay, so how do we get to those formulas? Okay, how do we get to those formulas? So the Skein module for, I made my gamma superscript there somehow, so it's something. My Skein module for my mapping torus, achieving it by taking the Skein category of the plane 2 torus and taking the Hochschild homology. But if you've twisted by this gamma and SL2Z, you need to take a twisted version of the Hochschild homology to do that. And then Hochschild homology and twisted version is Morita invariant. So replace the Skein category of the 2 torus, which we've come to understand, with something equivalent to it that's much easier algebra. And then the computing you take 0 there became not so hard. Okay. So theorem from the same paper of Gunningham-Jordan-Safronov. If we, and this is a more general setting of surface and reductive G, if you want the Skein module of surface cross S1, you take the Hochschild homology of the Skein category. Well, if you only have the Hochschild homology of the Skein algebra, don't, or the algebra versus the category, don't worry. But why does this make sense that crossing with a circle comes from Hochschild homology? Well, the Skein category is living in surface cross I. And here we have surface cross S1. Well, so that means I'm drawing my morphisms of surface cross I, and I might have an S above a G of something happening. When you do cross S1 and bring it around, right? We see this a lot in topology knot theory. Once we close it up, it's like taking a trace, right? This F can come and slide around, and it's like, oh, F after G or G after F, they become the same thing. And that relation is exactly what you're modeling out by when you compute zero Hochschild homology. So whether you, I mean, that's not a proof, but that's just saying it's totally believable. And when you do this twisted version for the mapping torus, you can twist this Hochschild homology formally, right? So instead of F after G versus G after F, one of those, so the F gets twisted by the stiffeomorphism. Yeah. That exactly matches up with the picture before, though, right? Of having stiffeomorphism come in when you join things up. So I think that's pretty believable as well. Okay, so what does that mean, right? So if we're just crossing S1 from the 2 torus, that's a 3 torus. So the Skein module of 2 torus, we get it from the Hochschild homology, the same category of 2 torus. And in previous work with Gunningham-Jordan, we proved that in the GLN case, the Skein category of the 2 torus is merged into the Skein algebra of the 2 torus. Well, that's great, because if you're not done, then you just computing Hochschild homology and algebra, you're going to have an easier time with. And I will say that is not true for FLN. So that's why these theorems, we have them for GLN so far and not yet SLN. SLN has more stuff. Okay. And then, it also worked with David and Sam, that Skein algebra is really equivalent to something else. What? Anti-spherical DAHA, double affine Hecke algebra type GLN as well. So don't worry about what the type GLN DAHA is. It's some known wonderful algebra that Schreck invented. And you take your sign idempotent, which we have that just lives in like the finite Hecke, which sort of has those pictures of, and you just take the corner rate, you just it's idempotent truncation of it. That's what you mean by anti-spherical. Anti, we can use the sign. You say spherical, we use the trivial idempotent. Okay, and it's not just any GLN DAHA, it has 2 parameters, a loop parameter, and quadratic parameter. And the quadratic parameter is our Q of like rect Q and so on. And the loop parameter is an appropriate power of it. All right, so Marita. Well then Marshall back in 99 had this shift sorry, I should say for the rational Schrödinger algebra, there's a shift isomorphism between spherical and anti-spherical shift parameters. That's rational Schrödinger, but it works at the DAHA level as well by Marshall. And so the anti-spherical DAHA at the loop and quadratic parameter is Marita equivalent. Actually, I wonder why I said Marita equivalent. They're isomorphic. They're isomorphic to a spherical, meaning this idempotent truncation is trivial of a DAHA where you keep the loop parameter the same and you change the quadratic parameter by something. Okay. And then we're putting in our particular special parameters that match up to the Skein algebra. When we do that, this new quadratic parameter becomes 1. Okay, so that means that we just put a 1 in there. And when you put a 1 in there, a 1 that for your Q minus Q inverse, right? A 1 over Q, that means it became symmetric. Okay, so that means that this algebra that we go down to, which has this trivial idempotent on either side, has something just with the symmetric group, and then there's a trivial line for the symmetric group. That means you're taking SN invariance of what you get, and what you get is what I'm calling the quantum torus. and. Okay, and then, right, so putting all of those theorems of boxing down, right? We go from category to algebra to anti-spherical DAHA, spherical DAHA at really nice perimeters, which just looks like the SN invariant quantum N torus, which also, if you wanted to say quantum N torus symmetric group. So we just have a chain of Morita equivalences here that we can say and just get to work with this algebra. It's a nice enough algebra, this quantum torus, that I'm gonna just show you what it actually is. So if I just had one copy of rank one quantum torus, I just have like Riemann expressions, x and y inverse, and they q commute with each other. Okay, q squared to make everything balanced. Yx is q squared, xy. And I can just tensor that together with itself n times, meaning I have m x's, n y's, and each x's commute with each other, y's commute with each other, x's and y's with different subscripts commute with each other. So like the subscript is the same, that they commute. And that's, well, then we have to smash that with the symmetric group and compute its Hochschild homology. That's not such a bad thing to do. Okay, so let me just give you sorry, I should say, you might have seen something very similar to this quantum torus smash Sn and then equals 2 case, because this is, I mentioned Brody also working with SL2, but that's not GL2, it's SL2. But it, you know, long ago using other technology had completed the Skein algebra there as the S2 invariance of a slightly different looking quantum torus, the SL version versus GL. But anyhow, coming back to it, and then another ingredient is when you take the Hochschild homology of an algebra smash and symmetric group, you can break that up as a sum of the conjugacy classes of taking the Hochschild homology of a particular bimodule where, well, on the left, you still have the action of A, and on the right, twist it by that symmetric development. And so let me just do review of Hochschild homology, which is in. Let me just do a couple of sample computations. Okay. So if we are an S2, so we have two Gaussian classes, identity, non-identity swap. So then you're modding out by these swap twist commutators. So if it's x1 and y2, you have x1, y2 minus y2, x1 twisted by your permutation. So that means x1 will become x2, and you have to straighten with your Q commutation. Okay, so you do that, and then just a couple of sample commutations. So if we were to take a commutator with like x1 inverse and x1, then what we get is 1 minus x1 over x2. We're modding out by these things. Okay, so let's say I have this degree 0 monomial. It's equivalent to 1. And I took some arbitrary monomial here, and I took the appropriate commutator, and just the end result is I got 1 minus q to some power times the monomial. That means we're killing monomials that are not degree 0. So as a very sketchy way, it should be believable that if we're just twisting by the symmetric group and we're putting in our quantum torus, you get something one-dimensional for all of your W's. This argument works. And we have partition of n many conjugacy classes. The symmetric group, and each thing gives dimension 1. So that's a quick and dirty proof that the dimensions for G GLN is that partition. And so you do the same thing now when you do this twisting by SL2. So if you twist by something in SL2Z, CD, it takes your x1 and replaces it with like x1 to the A, y1 to the B. Right, and y1, x1 to the c, y1 to the accompanied to CD. And so now you're going to mod out by these commutators where you twist by both your symmetric group element and your gamma, and they commute with each other on the end copies of the quantum torus. Right, so the gamma doesn't change the subscript. I could have said x2 and y2, the same thing would be happening. Okay, and so you do your twisted commutators, and again, so on the one hand, if W swaps y1, y2 And it's not y2, y1, it changes the subscript. And then gamma takes that and then changes with various powers. So this is the things we're mining out by. And I will just, okay, well, it comes down to, it's all about the exponents. It becomes all about the exponents on these vectors. And basically saying, look, when do I have, you know, some things zero out, and when do I have something equivalent to 1? If we just keep track of those exponents, that means we're just looking at maps from z plus c to the n, z plus c to the n, the x exponents and the y exponents. And it's just computing the cokernel of a very explicit matrix. And I think, yeah, even though I'm gonna take an extra minute. I think it's worthwhile. Right, so just briefly, right? So I wrote x, y to the u. So I'm packaging the x and the y exponents together, and u is a it's not an n long, it's a 2n long vector of positive and negative integers. And I have some other exponent v, right? And we do this commutator, right? The x and the y, all the subscripts in the x and the y change by w, and the exponents on them change by gamma. And so that means that if we ignore the powers of q after we straighten everything, on here we're going to have a total of u plus v. And on here we're going to have v plus u changed by w tensor gamma, which means if we feel it's u plus v plus this w gamma minus identity, you will have u plus v on both sides. So it's really, these things are being treated as zero. If these things are being treated as zero, it can mean that you want the co-kernel of the map from z plus c to z plus the n, which is this omega tensor gamma minus the identity. A little cartoon of it. I have a 3 cycle. I have a gamma, w tensor gamma, 3 cycles of gamma around. Any such thing, column reduces very nicely to something with a bunch of identities on here. And what are you getting here? Identity minus gamma cubed. In general, for a k cycle, identity minus gamma to the k. And if you say and then if you're doing further column reducing, the determinant of identity minus gamma to the k ends up being the numerical data that goes into counting how big that co-kernel is. So that's just some Smith normal form kind of theory. Yeah. And the determinant of identity minus gamma to the k is twice minus the trace of gamma to the k. So if you remember that formula for the CK in the Euler expansion, we have this trace minus 2 or 2 minus trace in absolute value. That's the ingredient. That's where it comes from. So it's just doing a bunch of column reducing and Smith normal forming. And we're just basically computing these co-kernel sizes there. And then I went through very quickly about when you have to smash product, the symmetric group, these Hochschild homologies on bimodules. I also wanted to get co-invariant with the centralizer of W, and that changes things a bit. Well, that doing those co-invariants comes to just a symmetric group, it's just an orbit count. It's just an orbit count, so we just use Burnside's formula, and that's where we get this formula. And then that's if it's an n cycle, if it's a product of many n, so different size cycles don't talk. The product of many n cycles, then if you think about your orbit counting, you understand what happens to the 3 cycle, but then I have kind of 4 identical copies from it. And if you think about how orbits work, that's like choosing a multi-set of 4, like 1 for each of identical piece, and that's this binomial coefficient, which explains why the exponent is just this sort of C3 of gamma. So this sort of explains why it fits together in that Euler expansion. So lots of data here of examples of the different. Oh, so you're asking about like the growth. So here's for an arbitrary matrix of trace 4. You can kind of see how the growth of the CKs go. It's a little small. It starts at 2 and goes like, the 1,000, 4,000, 15,000, and so on. So it grows. Another example, I would skip that.
Thank you very much. Questions, comments?
So do you always expect this kind of like possible formula for other three manifolds, or is it like just for manifold, right?
So if it's GLN, we conjecture that you would have some kind of nice Euler expansion. But not sure of the formula of how we would compute those CKs there. But yeah, for GLN, we do conjecture there should be a nice Euler expansion. But yeah, we don't know how to compute it because one of the big ingredients here was understanding what happened to two torus cross I. And so I'm not sure for how many other surfaces the scaling algebras are as well known.
So is this just the product over all 1/1 minus G to the I?
Oh, sorry, this example,
What did you leave out?
yeah. No, here, I didn't leave anything out, so I have, so the point is I left out, I left out a 4. Whoops. Yeah, I left out, one of these gets a 4 on it. I think it's the odd ones would be equal ones that get a 4. Let me, no, I did. Good catch. Good catch. So this is negative, it was 4, 1, 4, 1, 4, 1, 4, 1. And so the odds get a 4. Yeah, the odds get a 4.
So I had a question.
Yeah.
So at some point, if you were computing and you got this type of DAHA with T equals 1,
Yes.
what exactly?
So let's see. Here we go. Right, so
The category of scaling category two terms.
yeah, right, so the Skein category, the Skein category is where you put the Skein algebra. And the Skein, and this works in SLN or GLN if you put the appropriate SLN DAHA here. So the Skein algebra with the two torus is the anti-spherical DAHA at appropriate parameters. So the quadratic parameter will always be the cube, like for rep cube. The loop parameter will depend on it in some way.
Yeah, but when the shift it becomes a spherical DAHA.
And then
so here,
shift, so the shift isomorphism is between anti-spherical and spherical in either direction of the DAHA.
so this is for T equals 1 is really very simple, right?
Yes.
Because the McDonald polynomials just become monomials.
Yeah, monomials.
Symmetric monomials, isn't that right? And your theoretic operators, they're just raising to the Q power. I mean, the computing the Q degree.
I'd have to do that a little bit more slowly, but I'm willing, probably. Yeah, T equals 1 is just easy symmetric group. I thought it would be sure polynomials, but this one.
No, I feel it's because monomials. Q equals T, that I'm sure.
Q equals T, maybe for sure. Yes, I'm sorry, yes, Q, yes, okay. Then.
So, I mean, generally the spherical data is quite complicated, but in this situation, I think it's very simple.
It's just this SN invariance in the quantum torus.
But even the algebra structure should be very simple.
Yeah, algebra structures. Yeah, so you can just do. I mean, it's like taking like two variables. It's like taking two variable symmetric functions. Like diagonal. Any other questions?
If not, let us thank you. Yeah, I know.